The next uh, topic is check the following operators are Hermitian or not. Since we're discussing about operators, so many operators we're discussing, this Hermitian operator is very important in quantum mechanics. So we need to carefully check this operator whether it is yes or not. Okay. Definition of a Hermitian operator. Okay. So again, I'm going to write definition. Two inner products of vectors phi of x equal to a diagonal phi of x and phi of x. So this is the definition of Hermitian operator, right? So or we can write like this. Dirac rocket notations, wave function psi. This one is operator and wave function pi equal to this is a diagonal and wave function pi, and this one is a wave function psi and pi. Okay, so this is the basic definition of a Hermitian operator. If a diagonal equal to a, then we can call that operator Hermitian. Simply. So we can write this definition like this: integral minus infinity to plus infinity psi m complex a psi n into dx equal to integral minus infinity to plus infinity a psi m, okay, complex psi n dx, or minus infinity to plus infinity psi n complex a psi m dx whole complex. So if you apply complex, the A diagram whole diagram got here, right? A complex whole complex A, then that will change into the bra vector, bra will change to vector, then we can get this function. And this is exactly the notation. These two are same. So after applying this notation, this get vector changing into the bra vector, okay, bra vector changing into the get vector. So this is the integration definition. By using this formula, we are going to check these operators are the Hermitian operators or not. Okay. First, let us check the d by dx, right? So operator A d by dx is the Hermitian operator or not? So psi of x and d by dx, okay, pi x into dx, right? Minus infinity to plus infinity, that equal to d by dx psi of x complex comma phi of x dx integral minus infinity to plus infinity. We want to prove this one. So let us take this equation first. So after applying integration minus infinity to plus infinity, right? So it is better to write like this. That's right. Integral minus infinity to plus infinity psi complex of x d by dx of pi dx dx. So this is integral u dv, right? Here I am taking this one is the u, this one is dv. So u equal to psi complex of x and dv equal to d by dx of pi x, and then v equal to pi x, du equal to d by dx psi complex of x. Okay, so that equal to psi complex of x, phi complex phi of x minus infinity to plus infinity minus integral minus infinity to plus infinity d by dx phi of x pi of x into dx. Okay, so this term becomes to 0, right? And remaining term is like this, minus infinity to plus infinity minus d by dx, okay, psi complex of x comma pi of x dx. So we got this one after applying dagger d by dx whole dagger. I got minus d by dx. Therefore, so not Hermitian. It is a anti-Hermitian. So we know A dagger equal to A Hermitian. A dagger equal to minus A. This is anti-Hermitian. Okay. Next one is next example. Since d by dx is anti-Hermitian, then we can check easily this one. I d by dx is a Hermitian or not? Simply I am going to apply here I d by dx into whole dagger that equal to, if you apply dagger of this I, then we can get minus I. So if you apply dagger of the d by dx, then you can get minus dx. So that is equal to I d by dx. Therefore, I d by dx is Hermitian operator. So don't check this method. You need to follow this basic method. Okay, this is the basic method. You need to follow this thing. Next, this one is very important. Third example is very important. Let us look carefully. Operator A equal to dou by dou R. So if you apply this operator on diagram, then we can get dou by dou R minus dou by dou R. So where R is the radial coordinate in spherical polar coordinates. So we can check this Hermitian operator on. Okay. So I'm going to follow the fundamental rule. Psi of R and A, phi of R, since here using R radial coordinate, which is why I'm using the R. A psi of R, comma phi of R. So this is the basic definition of a Hermitian operator. Then try to write this thing into the in terms of integration form. Here operator is dou by dou R, right? Phi of R. So that equal to integral minus infinite. Sorry, integral 0 to integral 0 to. So here R is the integration limits vary to 0 to infinity. Radial coordinate. This one is psi R, comma dou by dou R, phi of R square into dr. So we can't write d by dr alone. So this is the radial coordinate. The volume of we know the volume of the radial coordinate R square dr. So dv is equal to R square dr sin theta d theta. D pi is there. So here I'm using R in place of R. So volume dv equal to R square dr sin theta d theta d pi, right? So this is the radial coordinate function terms. This is the angular. This is azimuthal. Okay. So here I'm using, try to solve this equation. So let us take u equal to R square I star of R dv equal to dou by dou R phi of R dr. So then v equal to phi of R then du equal to, so this is uv 2r psi complex of r plus r square constant d by dr psi complex of r into dr. That equal to r square psi complex of r right and pi of r, this is 0 to infinity limits, minus integral du, this entire thing, to r psi complex of r plus r square d by dr psi complex of r into dr. V, what is v? So this is pi and r into dr. So this term is 0. The remaining portion is integral minus 0 to infinity minus is the term, careful, 2r psi complex of r plus r square d by dr psi complex of r into pi of r dr. So I'm going to common the term, okay, and it is better to divide entire this thing. Integral 0 to infinity minus 2r plus r square into d by dr is there. That's right. D by dr psi complex of r pi of r dr. So I'm going to write this thing here like this, minus 2 divided by r minus dou by dou r. I want to divide these two terms into divide by r, then I can get this. So this is psi complex of r comma pi of r dr. So I didn't get dou by dou r diagonal equal to minus 2 divided by r minus dou by dou. This is the answer. Therefore, the radial coordinate dou by dou r is not Hermitian. This is very, very important. The next example is x d by dx. X is position, right? Position is Hermitian. We can easily apply. So they are giving a equal to x d by dx, right? So if you apply directly, so diagonal. So for example, this one is a cut, this one is bra, or this will change like this. Okay, then x diagonal, right? Since we know the d by dx is a minus d by dx, and x is the same. X position is a Hermitian operator. So therefore, this function is not a Hermitian operator. So because I got is minus, this is the anti-Hermitian operator. So you need to practice this Hermitian operator. Okay, I'm going to stop here.